Today's topic is realization of the FIR realization using the linear phase. So last class we have discussed about n is equals to odd, the structure for linear phase realization, and today we will discuss about if n is equals to even. The same structure we are discussing about, and this is a given difference equation. Solution is, first we have to check whether it's satisfying the linear phase relation or not. So this is a given impulse response. So give it as equation number 1. Now using so this is a impulse response and shifted impulses, right? So we have this h of n as, in terms of writing a sequence format of the given expression, that is at n is equals to 0, 1 by 2, then 1 by 3. At n is equals to 2, the coefficient is 1. At n is equals to 3, it is 1 by 4. At n is equals to 4, that is again 1 by 4. At n is equals to 5, coefficient or constant is 1, amplitude we can call. At n is equal to 6, it is 1 by 3. At n is equal to 7, it is 1 by 2. So this is h of 0 coefficient, h of 1, h of 2, h of 3, 4, h of 5, h of 6 and h of 7. So if you are identifying the length of the sequence, so how many samples we have? We have 8 samples. Therefore, n is equals to 8, that is even order FIR filter. For this even order FIR filter, again we have to design first we have to check the linear phase relationship, then we have to substitute in the jet transformation of impulse response, that is h of jet, thereby writing the transfer function. We know that for linear phase, condition is h of n is equals to h of n minus 1 minus n. Now we know 8 is equals to, n is equals to 8. So if I substitute the same, h of n is equals to 8 minus 1, that is 7 minus n. Let us consider n value starting from 0 to up to 7 n values. So if I substitute n is equal to 0, then h of 0 is equals to h of 7. Now from the previous analysis, we know what is h of 0 coefficient. H of 0 coefficient is equals to 1 by 2. Now here itself you can identify h of 0 coefficient is equals to h of 7. Next, h of 1 is equals to h of 6. Then h of 2 is equal to h of 5. And these two are equal, right? The same we are mentioning in terms of the linear phase formula. So h of 0 coefficient is equals to h of 7 coefficient, that is equals to 1 by 2. Then n is equals to 1, h of 1 is equals to h of 6, the coefficient is 1 by 3. If n is equals to 2, then h of 2 is equals to h of 7 minus 2, that is 5, is equals to 1. If n is equal to 3, then h of 3 is equals to h of 7 minus 3, that is h of 4. Therefore, the coefficient is 1 by 4. When n is equal to 7, we have seen that there is an extra factor which is h of n minus 3, which is a common in throughout the problem. But here there is no common term. So we have all equated coefficients for n is equals to 8. So given system satisfies the linear phase condition. So we know that h of n is our impulse response. If I apply the Z transformation, it will give in terms of Z domain. So the formula for h of Z is summation of n is equal to 0 to n minus 1, h of n into Z power minus n. And we also know that n is equals to 8, and substitute in this formula and elaborate the summation. N is equals to 0 to 8 minus 1, that is 7, h of n into Z power minus n. Now elaborate by substituting the n value starting from 0 to 7. So h of Z will be is equals to h of 0 plus n is equals to 1, n is equals to 2, up to so on, n is equal to the last value is 7. So substitute all the n values in the expression. Now from this expression we know that the first coefficient is equals to last coefficient. The coefficient of h of 0 is equals to h of 7, right? If I take the common, that is h of 0 from first term and last term, I have 1 plus Z power minus 7 plus, if I take h of 1 as a common from h of 1 and h of 6, then I have Z power minus 1 plus Z power minus 6. Now similarly take h of 2 common from third and last but 1/3. So we have h of 2 as a common, Z power minus 2 plus Z power minus 5. Now the last two terms, take h of 3 as a common, h of 3 as a common, then I have Z power minus 3 plus Z power minus 4. Now if I substitute all h of 0 coefficient, h of 0 is equals to 1 by 2, h of 1 is equals to 1 by 3, h of 2 that is equals to 1, and h of 3 is equals to 1 by 4. And therefore h of Z will be, again the h of Z, that is transfer function, I can write it down as output Z transformation by input Z transformation. So 1 by 2, 1 plus Z power minus 7 plus 1 by 3 Z power minus 1 plus Z power minus 6 plus 1 into Z power minus 2 plus Z power minus 5 plus 1 by 4 Z power minus 3 plus Z power minus 4. Now multiply this x of Z to the right hand side. Then I have y of Z is equals to 1 by 2 x of Z plus Z power minus 1 into x of Z plus 1 by 3, which is a constant, Z power minus 1 into x of Z plus Z power minus 6 into x of Z plus Z power minus 2 into, multiply by the input, Z power minus 5 into x of Z, and plus 1 by 4 Z power minus 3 x of Z. So each and every term will be multiplied by the x of Z. Now apply inverse Z transformation on both sides. So y of Z, if I apply the inverse Z transformation, it will become y of n. Z power minus 1 into x of Z becomes inverse Z transformation x of n minus 1. Similarly, and so on. So apply the inverse Z transformation on both sides. Final expression will be y of Z becomes y of n is equals to, you will have 1 by 2 x of n plus x of n minus 7 plus 1 by 3 x of n minus 1 plus x of n minus 6 plus x of n minus 2 plus x of n minus 5 plus 1 by 4 x of n minus 3 plus x of n minus 4. Now, so give it as equation number 2. Now realize using the linear phase realization. The input is x of n. Now this x of n is delayed by one sample, x of n minus 1. Again delayed by one more sample to generate x of n minus 2. Now how many delay elements I have to create? X of n minus 7. So again it is delayed by one more sample to generate x of n minus 3. And delayed by one more sample to generate x of n minus 4. And generate x of n minus 5, 6 and 7. Now you can see the difference between the last problem and this problem. When n is equals to odd, there is no delay element in this part. But here we have, if n is equals to even, then we have a delay element here itself. Okay. Now the very first term is x of n plus x of n minus 7. So all these are connected by adder. Now add. So here at this part we have a x of n. Add the x of n with x of n minus 7, 6, n minus 6, 7. This is 7. N minus 7. And the coefficient for this is, 1 by 2. Next, add x of n minus 1 with n minus 6 with the adder and represent the coefficient. What is the coefficient here? 1 by 3. Now, x of n minus 2 plus x of n minus 7. And the coefficient for this is 1. So here also you can write it down. It is as h of 0 and this coefficient as h of 1 and this is h of 2. Now here at this part we have x of n minus 3. So this x of n minus 3 is added with this x of n minus 4 and the coefficient is h of 3, that is equals to 1 by 4. Now towards the output side we are directing all these two towards the output side. Whether you can direct it towards the, so output may be, you can represent at this side or at this side. The structure is same. So these arrow marks are very important in order to give a direction between where the input is going towards the output. Next problem is based on the circuit. From the circuit we are finding out the transfer function. So this is a given circuit of FIR filter, and from this circuit we have to identify what is our general transfer function. Now the reverse process. So last problem we have a difference equation, thereby we have constructed our circuit. Now it is a reverse. We have a circuit, thereby we have to identify what is the transfer function will be. In the first, x of n is the input, here the y of n is the output. Now first x of n, just this is x of n, and here write down x of n minus 1, n minus 2, here it is n minus 3, n minus 4, and after this we have n minus 5, n minus 6, n minus 7, n minus 8 and n minus 9. Now based on this, write down the expression. So very first expression is x of n plus x of n minus 9 multiply by coefficient, this is 1 by 3. Second term in the expression as x of n minus 1 plus x of n minus 8 into 1 by 5. Okay. Similarly, you have to write down first expression by going back. Now y of n becomes, first we have first coefficient is 1 by 3 and the addition of x of n plus x of n minus 9 plus 1 by 5 into x of n minus 1 addition with x of n minus 8 plus 1 into x of n minus 2 added with x of n minus 7 plus 1.33 into x of n minus 3 added with x of n minus 6 plus the last term 2 by 5 x of n minus 4 added with x of n minus 5 plus 1 into x of n minus So based on the expression, we have to identify how many number of delay elements are there and what will be the last term. This is x of n minus 10, this is 9, 8, this is 7, it is 6 and it is the last term is x of n minus 5. So based on the given circuit, this is our given circuit, x of n minus 5, 4 and x of n minus 5. This x of n minus 5 is multiplied by the coefficient 1. The last one is x of n minus 10. Next is apply the Z transformation on both sides. If I apply y of n becomes y of z, 1 by 3 x of z plus z power minus 10 into x of z, because of delay is minus 10, plus 1 by 5 into z power minus 1 into x of z, z power minus 9 into x of z, plus z power minus 2 into x of z, plus z power minus 8 into x of z, and plus 1.33 into z power minus 3 into x of z, plus z power minus 7 into x of z. And the last value is plus 2 by 5. Now this is a Z transformation. So here x of z is there. If I take the common values, that is x of z as a common in all, x of z into the very first term is 1 by 2, 1 plus z power minus 10, plus second term is 1 by 3 z power minus 1 plus z power minus 9, plus 1 into z power minus 2 plus z power minus 8, plus 1.33 into z power minus 3 plus z power minus 7, plus 2 by 5 z power minus 4 plus z power minus 6, plus 1 into z power minus 5. Now this is in terms of multiplication. Take it to the LHS side. So therefore I have y of z by x of z, that is our transfer function h of z, is equals to 1 by 2, 1 plus z power minus 10 plus 1 by 3, and remaining all factors I am writing as it is. Now here also you can see the coefficient for all the terms are same. the common terms which are common, that is first term which is common to last term, next term with last but one, and so on. Now this is our h of z. While writing the same expression, take care about the coefficients. The coefficients are constant throughout the entire problem. Now to get the final impulse response, apply the inverse Z transformation on both sides. If I apply the inverse Z transformation, h of z becomes h of n is equals to 1 by 3. This becomes del of n plus del of n minus 10 plus 1 by 5 del of n minus 1 plus del of n minus 9 plus del of n minus 2 plus del of n minus 8 plus 1.33 del of n minus 3 plus del of n minus 7 plus 2 by 5 del of n minus 4 plus shifted impulse response plus del of n minus 5. Now therefore h of n is equals to 1 by 3 del of n plus 1 by 5 del of n minus 1 plus del of n minus 2. Rearrange all the functions. Del of 1.33 del of n minus 3 plus 2 by 5 del of n minus 4 plus del of n minus 5 plus n minus 6 with the coefficient of 2 by 5, n minus 7 with the coefficient of 1.33, and del of n minus 8 with the coefficient of 1 plus 1 by 5 del of n minus 9 plus 1 by 3 del of n minus 10. And this is our final impulse response. So for the given circuit, the impulse response of FIR filter is this one. Thank you.